In honor of the 411th anniversary of Galileo pointing his telescope to the planet Jupiter and discovering what are now known as the 4 Galilean moons, Europa, Ganymede, Callisto, and Io, we'll be doing a worked example here about the planet Jupiter and one of its moons, Io. But first, let's go ahead and state Newton's law of gravitation. Newton's law of gravitation can be expressed in an equation like this. The force of gravity is equal to Newton's universal gravitational constant times the mass of one object times the mass of another object divided by their separation distance squared. We could put that equation into words by saying the force of gravity is directly proportional to the product of the masses and inversely proportional to the separation distance squared, right? And so we see that both of those ideas are captured here, along with a constant of proportionality. So you kind of want to put that in your own words. The force of gravity is directly proportional to the product of the masses and inversely proportional to the separation distance squared. That's Newton's law of gravitation. All right, the question goes on to state planet Jupiter and one of its moons, Io, may be considered to be uniform spheres that are isolated in space. Jupiter has radius r and mean density rho. Io has mass lowercase m and is in a circular orbit about Jupiter with radius n r, as illustrated in figure 1.1. The time for Io to complete one orbit of Jupiter is t. Show that the time t is related to the mean density rho of Jupiter by the expression rho t squared equals 3 pi n cubed over g, where g is the gravitational constant. All right, so give us some room to work through that. Make sure to do right there. So keep in mind what we're considering here. We've got a spherical Jupiter, a spherical Io, separated some distance from the center of Jupiter that's expressed in terms of how many Jupiter radii away. Like here's one Jupiter radius, and a certain number of that distance, times that distance is Io's orbit. Think about Galileo 411 years ago discovering Io, and if you just watched it for a couple of days, you'd find that the period for the orbit of Io is 42.5 hours. Now, it'd be really tough to get the actual absolute values of the distances for the radius of Jupiter and the radius of the orbit, but perhaps just by looking at how big the planet Jupiter looks through the telescope and how far away the planet Io orbits, you'd be able to deduce the value of n. Right, so that's something that's observable just with a, really not that great of a telescope, one that existed centuries ago. You'd be able to get the value of n. You'd be able to get the value of t. The rest are just constants, and we can actually deduce something about the density of a planet just by looking at the orbital dynamics of one of its moons. And so that's pretty impressive if you think about the power of scientific knowledge, and that we can deduce conclusions that are otherwise inaccessible to us just by sort of thinking through the ideas. So let's go ahead and show that this expression is valid here. And the way that we're going to have to do that is by knowing something about a sphere and knowing something about circular orbit. So let's go ahead and put all those ideas out. It might be easier to work through it maybe right here, like on the margins of this figure here, so we can be mindful of what we're working with. In order for Io to go in a circle, there must be a force that's pushing it towards the center of the circle. We call that force a centripetal force, centripetal force. And it's equal to the mass of the thing doing the orbiting, right? And so we'll call this one lowercase m, Io. Now it's got some velocity sort of this way, tangential velocity v, that stays constant. It's accelerating because it's always changing its direction, right? So a short time later, it's going in this direction. A short time later, it's going in that direction. So it's constantly changing the direction of its velocity and therefore accelerating, even if its speed remains uniform. So centripetal force is mv squared over r, but the r in this problem is expressed like this in terms of Jupiter radii. So it's nr. So that's centripetal force, mv squared over r. R for this problem is n times capital R, where R is sort of this distance here. Centripetal force just tells us the direction of that force, right? It says it's center seeking, so it always points towards the center of the circle. It's provided by gravity. And we know that the equation for gravity is G m over r squared. And r in this case is still nr, the way they've expressed it here. So we say the centripetal force, which in general is mv squared over r, has to be provided by gravity here. And so we set those two equal to each other. Another idea that we need is the velocity of Io moving in this circular orbit is going to be distance over time. They've told us the time is just t, so we can leave that alone. But the distance we want to express in terms of other things, like where's that pi coming from? Well, we know that the distance around a circle is 2 pi r, but r here is nr. 2 pi nr over t is a way to describe the velocity. If we rewrite this equation, canceling out what we can, we realize that the mass of Io cancels. This nr cancels like one of those nr's in the denominator, and so we're left with velocity squared equal to Newton's gravitational constant times the mass of Jupiter divided by nr. Here we can now substitute this in for velocity. So velocity, you may recall, is 2 pi nr over t. We're going to square all of that, set it equal to gm over nr. So this becomes 4 pi squared n squared r squared over t squared equal to gm over nr. If we now realize that the mass is nowhere in the expression that we're trying to get to, but we recall that they told us this was a sphere, spherical Jupiter, and we need to introduce density into this also. We can recognize that just like in general, velocity is distance over time, density is mass over volume. Specific to this now, we've got the volume of a sphere, okay, with radius r. And so we'll rewrite this so that mass is the subject, m equals, and it's going to be density times volume. And the volume of a sphere is 4/3 pi r cubed, and r is just the radius of Jupiter itself here, right? So that's the volume. So rho times that volume is the mass, and we can substitute this expression in for m over here. So let's rewrite that. We've got 4 pi squared n squared r squared over t squared equal to g. And now the mass we're going to write as rho 4/3 pi r cubed. And we still had this nr down in the denominator. All right, so one of those radii, so r squared, is going to cancel out that. And so if I sort of rewrite this again, 4 pi squared n squared r squared over t squared equal to g rho 4 pi r squared over 3n. These r squareds are going to cancel, divide each side by r squared to show how they cancel. Let's move t squared over to the numerator over here and multiply both sides by t squared to cancel it. Now we've got our rho t squared together, and we just need to get rid of all this other stuff on this side of the equation. So I want to divide by a g to get rid of that. I want to multiply by a 3n to get rid of those. I want to divide by a 4, right, to get rid of that, and divide by a pi. Right, so then the 4 goes, so the 4s will cancel, the g's will cancel, the pi's cancel. Ooh, it's always a shame canceling pi. And then the 3n's go away too, and we're left with a rho t squared. And so we get, finally, rho t squared equal to, so remember, I'm just sort of keeping these on this side. If I multiply this side of the equation by this, because it's convenient to sort of cancel out everything, I just got to do it to this side over here. So on that side, I would have multiplied by the factor 3n over 4g pi to keep the equation equal, and I still have all this stuff over here, 4 pi squared n squared. Right, I already canceled out with t squared, and the r squared is already canceled. The 4s are going to cancel. One more cancellation of pi, and then the n's combine to become n cubed. And so we get our final expression, rho t squared equal to 3n cubed times the pi divided by g. And that certainly agrees with this over here. You know, you can write the pi in whatever order you want to. So rho t squared equals 3 pi n cubed over g, the same thing that we get when we just sort of consider circular motion, spherical objects expressed in terms of the variables that they present. So nice, those are 4 marks right there for that bit of work. The question goes on to give us some data. And it says the radius r of Jupiter is given, the distance between the centers of Jupiter and Io also given. Note that it's sort of like a whole order of magnitude bigger, 10 to the 5 compared to 10 to the 4. And they give us the period, but the period is in hours. We want to calculate now the mean density rho of Jupiter. And so we can remind ourselves that we just had rho t squared equal to, what was it, 3 pi n cubed over g. And so right away, we can just kind of move the t squared down there. Okay, so divide each side by t squared so that rho is the subject. And we can first calculate n by saying, how many times, do we multiply this number by until it gets to be this big, right? You may recall that nr, okay, is the total distance between Jupiter and Io expressed in terms of Jupiter radii. We've got the Jupiter radius here. So nr, the product of n and r, is equal to this number. So nr equals 4.32 times 10 to the 5. And r we can plug in like we know that. So we got 7.15 by 10 to the 4 kilometers times some number n to give us the nr, the product, 4.32 by 10 to the 5 kilometers. Here, we don't need to convert to meters because the units are just going to cancel, right? We're effectively just saying, how many times does this go into that? To get how many times, Jupiter's radius do we need to go out until we're at Io? So dividing each side by this. You did that in your calculator, you could prove that it's about 6. There's about 6 times the Jupiter radius to get to Io's orbit. And so now we know that n is equal to 6, and t is given to us in hours. And so, Galileo, 411 years ago to the day, would have been able to, well, maybe it'd take him 2 days, right? Because that's more than 24 hours. So I keep looking at it and eventually realize, okay, hours is a sensible unit to sort of measure this in. But because we're using g, Newton's universal gravitational constant, we know that we're restricted to certain units. And so g is 6.67 by 10 to the negative 11, but the units are Newton meters squared per kilogram squared. And we know that within a Newton, because F equals ma, a Newton of force is really a kilogram meter per second squared, right? So that's where the seconds come in for the acceleration, embedded within this unit, the Newton. So we've got to convert this into seconds. And so we could simply take our 42.5 hours and set up a conversion where we know that there's 3,600 seconds per hour, and we just multiply those. It's been a while since I've practiced my mental math, and so I'm going to go ahead and multiply 3,600 by 42.5 in my head, 153,000. But you all can use a calculator if you want to. Hours cancel, I'm in seconds. So 42.5 hours is 153,000 seconds. We got everything we need now to plug it in and solve. So rho equals 3 pi n is 6 cubed over g, which is this value still. I won't worry about the units so much because I know I've already taken care of them. They give me kilograms per cubic meter. The SI units in, the SI units out. At the time I need to plug in is 153,000. And don't forget to square that. Let's see this one on the screen. Here's the calculator. Go to a spot for it, maybe. All right, maybe you can see it there more clearly. So I got 3 times 5 times 6 I know that's inefficient. All right, so there's my numerator divided by these grouping symbols, 6.67 and raised to the 11 equals divided by 153,000 squared. And I get a density for the planet Jupiter of 1,303, which I would just round to 1,300. All right, so there's 1,300 kilograms per cubic meter in the planet Jupiter. Note again that we're able to deduce the composition of this planet, which is 5 times further away from the sun than we are, just by looking at a moon through a telescope and basically realizing how far away it is compared to the size of Jupiter and how long it takes to orbit. Right? Those are the only things that we needed once we worked through the math and saw, oh, we can express the density in terms of those things. So that's a pretty powerful way to think. The last part of this question in the final mark reads, the Earth has a mean density of 5.5 by 10 to the 3. So instead of 1,300 for Jupiter, it's 5,500 for Earth. It is said to be a planet made of rock. Wouldn't you know that's what's said of the planet Earth? It's this planet that's said to be made of rock. I can look outside my classroom window and visually confirm that. Yep, I see rocks on the ground. We are on planet Earth and it is a rocky planet. Good. By reference to your answer in one, comment on the possible composition of Jupiter. And so here we want to say, because the density is so much lower, it's made of a material that is less dense than rock. That's a very safe way of putting it, sort of in terms of the science. You may take it a step further and go, well, maybe it's made of something like a gas. Gases are less dense than solid rocks, right? And we already kind of know something about the planet Jupiter, right? We study it since elementary school, that we know it's one of the gas giants, right? And so this is just a way to sort of show mathematically, to sort of quantitatively show what the density is and how much lower it is than that of Earth. This is then a 10-mark worked example question with Dr. Schleich. We'll see you next time.